Our project is the CPI Temporal Network Analysis. The primary objective is simple: to compare the prices of products between cities over time. Using these comparisons, we aim to identify cities with similar pricing and identify and correct anomalies to ensure uniform pricing across the entire country. We sourced our data from the Pakistan Bureau of Statistics. Our motivation for using cosine similarity and network analysis is that simple price comparisons don't reveal structural relationships. The analysis is founded on a four-step process. Firstly, we had to handle the raw data. After scraping the data to sort differently named products, we assigned them to one of our seven major categories: food staple, utilities, etc. We then handled the missing months by substituting the average price of the other months. Next came vector construction. We took the average price of all products within a category across a year and used this to form a 7D CPI vector for each city, where each entry represents the average price for one of the seven categories. We then normalize this vector by dividing each entry by the square of the sum of all entries equivalent to the vector's length. To quantify the similarity, we use the cosine similarity function between the category components of each pair of the city vectors. This calculated the angle between them, giving us a score between 0 and 1 that indicated how synchronized the category prices were. We then constructed our graph using a similarity threshold by creating an edge between the two cities. For example, as we increase the threshold to zero point 0.9 for the clothing and miscellaneous network, the city of Khuzdar lost all its edges, illustrating its isolation as a clear price anomaly. Finally, we manipulated the graph using weighted edges. We assigned the raw cosine similarity score itself as the weight for each edge. This is crucial because it allowed our analysis to measure influence based on the strength of price synchronization, which is essential when calculating the centralities for our custom and correlation based weighting schemes.
This is the program we use to clean our data. First, we put all the common names of each category into one array. Then we imported each product and cleaned it by removing the brackets, by removing the measurements and everything. Then we did an exact matching by the keyword. And if we did not find it from the keyword, then we did a fuzzy match, which basically compared it with each category and just put it into the best category we had. After this is our main function, where first we imported everything. This is the styling. This is CSS styles, which we use for styling everything, the padding and the colors and everything. This is a function to read the CSV files. We made everything into CSV files as it's easier. Then this is the function to build the city vectors. And over here we can see the function to compute the cosine similarity. This is the thresholded matrix where similarity is only used when it is greater than the current threshold. And we fill the diagonal with 0. And this is the function to make the graph from the adjacency matrix. We can see that if it's a weighted graph, we add an edge with the weight. Otherwise, we add it without the weight. This is the centrality function, which computes each centrality. And then, as you can see, we have a function to aggregate the weights, where we are multiplying W. W is the weight of each specific centrality. After that, if I go down, this is all we use Plotly for all the for making all the graphs. We can see over here we use NX to build the network graphs and Plotly to make all the bar graphs. And finally, if I go in down to the main run analysis function, over here, this basically does everything. We see the total steps are for each category multiplied by how many years we have. And then for each category, for each year, we get its weight, we get the range, we build all the vectors, we take the similarity, we build all the graphs, we compute all the centralities, aggregate everything, build all diagrams and display the results. And we have everything into separate tabs so that it's easier to navigate. This is our visualizer for everything. As we selected the category clothing and miscellaneous for 2024, this is the raw cosine similarity graph, where basically if they had a similarity, everything was connected with equally. However, if I go only to above the threshold, we can see that Khuzdar, for example, only has 1 degree above the threshold. Over here, I can increase or decrease the threshold. Like if I decrease the threshold and then run it again, we can see that now there are a lot more edges connected. If I go back to the same old threshold, and over here we can see the heat maps. This is the heat map. As you can see, Khuzdar has the least with anything, and it also receives the least edges and it gives the least edges. And this is the centralities. If I can sort by each centrality, but if I go by overall centrality, Faisalabad has 1 degree centrality, one closeness centrality, 0.06 betweenness, and 0.25 eigenvector. And since it was equal weights, it had the highest score. And this is the influence score. As you can see, the top city it gave was Faisalabad. This is the Hesse diagram. Uh, for right now, it's just one category. But over here, if I do analyze all categories, and then I run the analysis again, we can see this is a Hasse diagram made, and we can confirm that it's reflexive, antisymmetric, and transitive. And finally, if I change the weighting for the influence scores, over here, I go to customize each category's importance. And over here, I increase the importance of fruits and vegetables by a lot. And then I run the analysis again. And now you can see is and I can see it's evident that Gujranwala is at the top, whereas before Faisalabad was at the top. This is because maybe it had the most similarity with specific regards to fruits and vegetables, which I increased by a lot. If I decrease it and increase non-food essentials, we can see the rankings change again. Yep, we can see Quetta has the most ranking.
Now that we have visually explored the networks and rankings, I'll explain what our analysis reveals. So, the weighted centrality aggregation demonstrated the impact of prioritizing one structure role over others, while the underlying network structure remains fixed. The rankings shift dramatically. So, we compare the clothing and miscellaneous 2024 network at threshold zero point 0.9 under the equal weights baseline. If you see Multan, it was ranked number 5. However, if we set custom scheme where we prioritize betweenness centrality with zero point 0.7 weight, Multan jumps from rank 5 to rank 2, which tells us that Multan's structural position as a price transit point becomes the most important factor when it comes to defining influence, even if its general price similarity is lower. So, coming to the effect of threshold variation on city clusters, the similarity threshold is a very crucial parameter as it defines the strictness of price linkage, and it also reveals meaningful economic clusters. So, for example, at a load threshold, the clothing and miscellaneous 2024 network is very dense with a density of 0.91. And as we increase the threshold to zero point 0.9, the network becomes very sparse. The density is 0.375. If you look at the city of Khuzdar, it becomes completely isolated. This structure isolation interprets Khuzdar as the price anomaly, which its price movements are highly unique and they're not synchronized with the rest of the network. Coming to reasons for the change in centrality scores, our four centrality measures assign a distinct economic role to each cities. So if you see at Food Staples and Grains 2023 network with a threshold of zero point 0.9, the city which is at the top is Faisalabad, which means that it is a highly connected region with the broadest price synchronization links. But if we see the top city for betweenness centrality, then it is Multan. So this distinction emphasizes that influence is defined by the type of connection a city holds. Finally, we model the temporal evolution of city relationships using the temporal partial order relation, where a relation exists if the edges of one network are a subset of the edges of another. The Hayes diagram and edge count reveals that the food staples and greens, the network dramatically grew from 57 edges in 2023 to 121 edges in 2024. This continuous path suggests a clear pattern of increasing price synchronization in the food staple market over the year. In summary, our project successfully modeled city price alignment using discrete structures. We demonstrated that the chosen mathematical parameters are critical in identifying influential cities and price anomalies. A practical application involves modifying the dataset for prices at motorway service stops, where a network analysis can instantly identify significant price outliers and critical intermediaries.